with an oscillating boundary part. And this is a joint work with Professor Nandakumar. He's also in the talk, so we will have lots of opportunity to learn something new. This is about a stochastic homogenization. And in fact, if I remember correctly, Professor Igor also talked about something on this topic. So Sankar, floor is yours. Kindly,
Okay.
you have 50-55 minutes, and then we will have last 5 to 10 minutes for the comments.
Okay. Thank you for the
Okay.
invitation, Dr. Ravi Prakash. So uh, we are going to discuss about the heat equation and the random evolving boundary domains. So let me go to the next slide. So so here the randomness comes from the boundary part, boundary that sorry. Uh, so it comes from the boundary of the domain, the spatial domain, which is also depending on time variable. So it's not the cylindrical domain when you consider to solve the heat equation. It's a non-cylindrical domain, but on the evolving boundary, there is an oscillation which comes from the random field, random variable. So the boundary condition I kept it here in homogeneous boundary condition with the boundary which is interface if you want to solve the solid equation and the fluid equation. So the velocity of the interface has to be matched on the boundary. So this is the condition we kept it. But yeah, that's one advantage to solve this equation. Though this work has been published with Professor A.K. Nandakumara recently in mathematical methods and mathematical method and applied sciences. So I'll there are related works, similar works, but which is different because they consider uh, the domain which is the porous media and the evolving interface kind of work. There has been like work with started with Peter. So it's carried on by Adrian Montaigne and his collaborators. So these are the works which is related to this type of work. But yeah, they consider the full domain, and they consider more regularity on the interface, which is known by knowing that they carried on this type of homogenization work and existence uniqueness work. So let me go to the that how to define the random variable. So first, so I'll define the probability space. And the probability space, we need dynamical system to have the structure, the differential structure when you want to do it. So we will have the n-1 dynamical system because I am considering the boundary part which comes from the lower dimension, which means n-1. In case 2 dimension, it's 1 dimension. So there is a restriction I put it. This can be changed. These constants can be changed, but yeah, this is the minimum one I kept it so that the domain do not split in case there are two type of functions in the random variable. So I'll define explicitly some examples so that we'll know how to define. This is the probability space, but of course I keep the time variable here, time interval. So for a random variable, we can define the corresponding random functions via this map, which is through by dynamical system. So this is how we define. That's how we introduce the Euclidean space structure in the random variable. So the corresponding realizations, that means for each fixed event, small omega. So we will have the functions, two functions from Rn minus time interval to R, which is defined by this way. So the profile I'm going to take it, the oscillating boundary. The special form, one is the eta omega, that random function eta, kept the bold eta, times the small oscillating part. So this is this separating the two functions, which is in fact we can take this eta omega to be a deterministic function which is independent of the event omega. So that will also work, but I took general case. So what I mean by dynamical system on the probability space. So it will satisfy the map tau, which is having the family of maps, comes from, sorry, yeah, I'll define it from here. So which is defined on omega to omega, sorry, O to O. So which will satisfy these conditions, two conditions, and it will preserve the measure for any measurable set from the sigma algebra of the probability space. And the map, the composition, so this map, the new map in terms of the dynamical system is measurable, but here with respect to the product sigma algebra. So when we want to say something dynamical system is ergodic, that means the invariant sets, measurable sets, which is invariant. When we call it it's invariant, which means it takes the same set. So in that case, the probability either 0 or 1. In other words, we can say in terms of invariant function, when we say invariant function is constant, then we will say that it's ergodic. There are two, like in other words, these are two equivalent definitions. And random variable, when this is important because when you want to do homogenization, we need statistically homogeneous condition, which means the random function given by the random variable via dynamical system, some dynamical system. That's what. So that is called the statistically homogeneous random variable. So this is needed in our case because we want to apply Birkhoff ergodic theorem. So before that, I need some terminology that is used in Birkhoff ergodic theorem. So for any function which is in L1 RD, the mean value, the spatial average, is denoted by this function. But this is true for any bounded measurable set of RD, any bounded measurable set. And mathematical expectation, I am denoting the script E. So which is defined by the integral over probability measure over O with respect to the probability measure. So now this, as I told earlier, the realizations we can define it via fixing the event to small omega. So when the function belongs to the LP space of with respect to the probability measure here, so I'm avoiding because it's a lot of notation will include with respect to the probability measure. If it belongs to LP, p greater than 1, then the corresponding realization belongs to LP log, not the full Rn minus 1, but it's a locally. And the convergence, suppose the sequence of function converges in LP of O, then the corresponding realization also converges in the locally in LP of Rn. It's any Rn, but yeah, we are here dealing with the n minus 1 dynamical system, so we are in Rn minus 1. So there are corresponding Sobolev space are the kind of generalized Sobolev spaces available in this case with respect to the LP omega. So So this following result is hold when this is random function. This is only comes from the random variable. So this derivative with respect to the semigroup generated by the one parameter semigroups generated by these operators. So and the gradient operator also, like, it will satisfy this from this definition. So this is important because we want to, like, given the random function, we want to model the problem via realization. So when you want to realization, then you need to take derivative with respect to the random functions also. So this is very important. Next, for example, like how we are going to, like, construct examples like random function from some examples, like well-known examples. Suppose we want to take a checkerboard, chessboard kind of things with a black and gray or black and white. So in that case, we need to construct the measure space, corresponding measure space, and the corresponding measure and dynamical system, so that we will have the oscillating domain on the black and gray different oscillations. So for that, take that, because we are going to take only two samples events, so that black and gray, and then we define the measure on the sigma algebra generated by these two. Because it's a discrete, we will take the 2 power O, so it includes everything, all the subsets. So how to define? We will define when the event is black, we will define P. When the event is gray, 1 minus P, so that its whole set will have the probability 1, and whatever it's less than, if all the other sets will have the less than 1. So P, that's why we need to take P belongs to 0 to 1. So you can take any P in between these two in this interval. So now I'll define the function, which is not a random function, but which comes from the choices here, which is, so the variables are from the torus t and 0 to t. So how we will define? On black, we will define some function eta 1 tilde, and gray you will define eta 2 tilde. But remember, I want to define the oscillating boundary, so I need to be careful so that the edges joins, like. So what I need to do is, like, I need to keep the edges coincides on the edges. So, and this -1 to 0, I took it because I took earlier the eta 1, that oscillating profile, which is between the -1 to 0. So for that we need to fix. Once you change there, you need to change everywhere, like corresponding places. So this is the discrete space, but we can't define it in discrete space because we need to have the continuous profile. So, and dynamical system also has to be, like, satisfied. So what we need to do, we will construct new probability space which comes from the the product space of the construction what we did. So each profile, say you in the one dimension, you divide 0 to 1 interval, unit interval to everything, and keep gray and white, or black and gray. So so you need to construct this product space so that it will have the measure preserving and still its probability measure. So everything will be satisfied in this case. So, and not only that, because we need to have the dilation we need to do. So we need to have this torus in one dimension with 0 to 1 interval. So corresponding the sigma algebra product and the measures also. So the element in omega hat, how I'm going to denote it, I'll just label it j, that integer label. So then the dynamical system on this discrete space, I'll define the following way so that it will satisfy the dynamical system conditions. So when it's a 0, it will remain 0. So when you add and like interchange, it will still be there. So on other properties also it will satisfy. So that's how we are defining it here. And remember, depending on this choice, we can change this choice by like introducing 2 dimension inside some circle, and you can choose this as a angled rotation, this set. Instead of discrete, you can choose continuous set also, but accordingly you need to define all those, like make sure that it will define everything like the properly, so that it will define dynamical system. This you can change like lot. You can introduce a random radius, random center. So accordingly we need to change the sample space. So once you define this, now we want to define the dynamical system on the torus T. So for that we need to have this integer decomposition. For any r y at in R, we will have the unique decomposition, integer part and the rational part. That's remainder part. You can say not rational, remainder part. So which, because it's once you have integer, then this belongs to the 0 to 1 interval. That means it belongs to T. That's how we can decompose this. And the corresponding the dynamical system, which is standard. So for any V on T, so you define this way, sum of the two terms and the separate with the integer part. So it will be belongs to the T. So it's both are like you can easily, one can check everything, like there will be calculations a little more, like you can check both are measure percent ergodic dynamical system. Now, so we want to define the dynamical system on the probability space, this space. So how we can define is like, now the terms are in omega as two terms, like omega hat and V. Omega hat belongs to the omega O hat and V belongs to T, the product space. So how we can define is the corresponding integer part with omega hat here with this V, and the K, that is second part, is the continuous dynamical system, which by the way we define the K hat. Term with the minus of the integer, so it still belongs to the T. So this is also like once you have those two things, like product of measure preserving is again it will preserve the measure, and the dynamical system satisfies everything. It's also ergodic. We can check directly. We can check. So now I want to define eta 1. That our aim, my aim is to define this eta 1, O to R, O cross 0 to TR. So how we are going to define is, we defined already in terms of the functions eta 1 corresponding the black and white. So which you can define by for first term. Small omega is the sequence and the V. So the sequence will take the first term, 0 term, and consequently that corresponding dynamical system, how it acts, by definition the construction eta 1 omega tilde, but the integer part it will come here, the sum of the y hat and V, because it will have two part, right? Omega will have two part, V comma T. So, and so correspondingly here also it will change, because we have the integer part, and we need to like go to the 0 to 1 interval, so we need to keep this definition and t. That's how we define. This is how we can construct, but this construction, once you change the sample space, you will get a different model and different measure space and different ergodic proof that whatever we want to do. So for example, I took both are random variable, eta and eta1 both are random variable, but for simplicity we may take this as a deterministic function. And remember, I chose eta1 and eta2 so that it will edges will coincide. So for that we need to have this restriction, this on the edges of 0 to 1 interval. So this is one particular example. We can choose anything which is vanishing on the boundary, so it will have the bump, and correspondingly later, so that edges will coincide. But this is a simple periodic function, so this is one choice. And this condition is needed because I assumed some interval. So if you want to keep in some interval, correspondingly you need to choose the constant here. If you want to increase the interval, say more, if you are taking the bigger domain, like. So this is the this case. In this case, eta is a deterministic function. That is the the curve which comes here this way, and the black part will have the oscillation, different oscillation, and the gray part will have the oscillation different scale, like you can see from here. And this choice is random, which can be changed, but only I kept it one slide, but you can change. That's how randomness comes in this profile. So another example, which is easy because we'll take the continuous two-dimensional torus and the corresponding sigma algebra, and because in the torus the probability measure is Lebesgue measure you can take. Now you can choose any matrix corresponding the matrix. Here we took 2 dimensions, so we will take a 2 cross 2 matrix. The dynamical system is defined by this way. It acts, but we need to take mod 1. Whatever it takes goes out, so we'll take mod 1. The same way what we did in the previous case, we are taking mod 1, so it remains in the torus T2. So obviously this preserves the measure, and dynamical system is ergodic, but here we need conditions. So this, depending on the matrix, it will change. So this has to be non-zero for any k, non-zero. K belongs to Z2. So so when this type of functions, so this is any periodic function, the realization becomes this way, right? Because from the random space we want to take it the realization form, so it will have this form, omega plus gamma eta y, eta hat. So this has the special name when the eta is continuous functions, quasi-periodic functions. This way, like we have the lot of problems one can fit into these cases, random models. So here, for example, here the choice eta I took is a particular constant 3 by 2, and the diagonal matrix is also diagonal matrix 1 root 2. So the realization becomes this way. See here, even though it's separating the omega 1 and omega 2 in 2 dimension, but it will like mingle here with via the gamma. So this is another example. So this way you can, like a lot of example will fit in this form, in this model. So now, so this is very important result, at least in our case, like when you want to do homogenization. So we need some convergence of oscillating functions. In this case, the realization will have the oscillations, but via dynamical system. So for any function in LPO, which is a random space, probability space, so the this is the dynamic, this is realization of phi. This is the realization of phi. Then which the realization will weakly converges to the average function. So in locally in Rn minus 1, this is what we want. Of course, this case it depends on the events. So which is holds for almost all event. Omega belongs to O. So also this average is tau invariant function, which means this conditions. When I said that ergodicity, when I define it, so whenever the function is tau invariant functions always constant when we say it's ergodic. So this is invariant function. We did not assume here ergodicity till now. So the expectation will satisfy this. Expectation of I equal to the expectation of the average function. So when in addition, when you assume that the dynamical system is ergodic, then this weak convergence, the realization weak convergence converges to this. But if you look at here, this is nothing but the constant in terms of event. So you integrated already. So which means it's not, the limit does not depend on the event omega. So it's a constant. It is a deterministic function in this case, but still it's in LP log Rn minus 1. Okay, this result is like we will use it, but of course if you remember, I define it even though we can take it tau to be ergodic function, ergodic dynamical system, but the first part eta, the capital eta, sorry, not capital eta, the bold eta, which is also depending on the event. So doesn't matter you take ergodic or not, but anyway our problem will depend on the event. So from the ergodic theorem, Birkhoff ergodic theorem, we will have the realization of derivative of the realization eta 1, that with the oscillation, right? This is how we define it, which will weakly converges to the average function. But by definition, the average function of eta 1 with respect to y, y will have the n minus 1 variable, right? Y will have n minus 1 variable. So this integral becomes 0. So that's how like we will get it. This we will use it because there won't be any contribution from eta 1 and the limit problem. So now even though I took the problem on the oscillating boundary will have the random dependence, but I don't want to take the data from the random part. So for that reason, I took the again non-cylindrical domain, but I took the maximum of omega x hat and y hat, so that it only depends on eta, this function. Sorry, it depends on only t. So in this case, this still it's a non-cylindrical domain, but it's bigger than the random non-cylindrical domain. So corresponding non-cylindrical cylinder is look like this from the definition. So it contains q epsilon t for all epsilon. So I'll take the data from this space, non-cylindrical space, which is like instead of coming from the reference domain, the data we will take data which is non-cylindrical domain. So which in a sense it's a generalizes. So it's always other case, like when you're coming from the reference domain, you'll always get this option. You can extend to the bigger domain and work on problems. So, but yeah, there should be a condition because we are defining the boundary via the random variables. So we need to keep the some conditions so that it's well defined our problem. So this is comes from we need at least Lipschitz condition. So this and when I do the change of variable to the reference domain and the derivative occurs in the coefficients, so we need this condition for to do the homogenization. This part comes from again because it will have the coefficient will have these two parts also. So derivative of eta with respect to t. But remember, this is not the normal Euclidean derivative. So which is comes from the one parameter group generated functions generators. So this hypothesis is made, and now so what we want to do is like we'll go to the reference domain. So the corresponding so when you want to do the go to the reference domain, we'll do the change of variable here, which the unit cube which translated to this way so that it's fit into the our domain, that non-cylindrical domain. So qt this is the map that which is you can see from these two conditions, which is Lipschitz transformation, Lipschitz diffeomorphism, you can say. So but yeah, here remember this is realization of these two functions, bold eta and eta 1. So we want to like look at the differential equation on the reference domain. So how we will go, we define correspondingly, like you are looking the inverse part, like coming back to the reference domain. So we define capital U epsilon as the solution in the reference domain via this definition. And the data, remember, data we took even though independent of event omega, but still f epsilon will depend on random variable. So now you'll understand why the choices are built. Like otherwise you can take f from the reference domain you via inverse map, this inverse of this map, and when you come back it will be fixed. So it's better you take on the non-cylindrical domain. So this is the differential equation, the transformed differential equation on reference domain. So here even I told you, right, I took a choice for this inhomogeneous boundary condition. I'll take it a homogeneous boundary condition here onwards, because we have already discussed the inhomogeneous part, how to lift the homogeneous boundary part boundary condition via the lifting, the parabolic lifting. You can do it with the minimal condition. So here onwards I'll remove this. I'll make it homogeneous. Here remember earlier it is still Laplacian, but now it becomes oscillating coefficient function. But it is a special form. There are like look at here this in minus 1. So the contributions are coming from the derivative of eta epsilon. So we need to show this is uniformly elliptic, which is always possible via you can do both way. You can directly show this is uniformly elliptic via some diagonalization form, sure diagonalization, or via use this m epsilon transpose, which comes from, sorry, I missed it to define this. Okay, there is a form like only here and this term, here this term. So there will be like a contribution from like a upper triangular and lower triangular form. So you can see from there that the diagonals are strictly positive. So from there you can show this is uniformly elliptic. Okay, now see here this term, when you do the change of variable, there will be eta epsilon in front of the divergence. We want to study the weak solution, so this has to be either transformed to the test function, or you multiply eta epsilon so that the test function with eta epsilon so that it will cancel. So you do integration by parts, but in that case, there will be eta epsilon which is time dependent here. So when you want to do existence and uniqueness part, this will have some matrix in the Galerkin formulation. So still it will go through, but one has to like shift it to show this matrix. It's not the identity matrix what you get in classical problems, because here there will be a matrix which depends on time. So you need to shift it to show in a discrete level, that in finite dimensional ODE problem. So so this is how we can define. But another way is like you throw this away, but there will be extra terms from here. It will come derivative of the eta epsilon, 1 over derivative of eta epsilon here, the product. So that has to be taken outside. Another term will come. So there are two ways you can do it. So existence and uniqueness, from the Galerkin method, you can show this. The solution which is bounded by the data, but the C which is independent of both epsilon and the event omega, that random variable. Once we have this, then you take expectation, you will get this. But here remember, this will have the event that it depends on the randomness, right? Both f epsilon and h epsilon. So you need to go to the original domain, that what we took, f and h, that both are from q hat t, right? Q hat t and omega hat 0. So that's how this constant extra one will come. So still you can, that's easy part. And even though I took it the fixed function as a data, but as we noticed earlier, it f epsilon and h epsilon both are there. So corresponding random function here also, look at the randomness, how it comes from the corresponding the transformation with respect to eta w1 omega only. So this is how it comes out. So we will have the convergence for almost all omega, the following convergence: f epsilon converges strongly and h epsilon converges, because we took the fixed function. So in case of, so I want to recall something. In case of random homogenization, once you have the probability space and you want to solve the cell problem, when you want to use two scale or some other two scale methods, say you want to do two scale convergence, in that case it will have the cell problem, which is in case we know how to solve in cell problem in the cell, but now we are in probability space. So there is a way to like solve it via Weil decomposition. So the problem becomes, now we want to solve on the probability space. We need to find some function which is dependent for any given in Rn. In earlier cases, what we do in periodic cases, which depends on the cell, say y, which is you choose in cell itself. But now we need to choose an Rn. This I wrote it Rn because we are solving an n-dimensional problem. So correspondingly, you need to like all the derivative, the nth derivative, you make it 0. The 0 as a operator. So that's how we need to do here. So this is the cell problem we want to solve. Auxiliary problem, not cell problem, because it is not in the cell, so it's called auxiliary problems. So we need to find V psi in the potential space, that potential function that for a given n vector, we need to find a g. So v is nothing but the gradient of g. So this is the potential, that's why the part, and the solenoidal space, the grid. This is the definition for that with respect to L2 omega n. So the closure. So this domain is the domain of all the generators. So this intersection of all the generators, domains of all the generators. So the effective coefficient in case of elliptic problem will be computed by this. So but I am not going to use two scale convergence. We can avoid this auxiliary problem in at least in our case, because there is a special form for matrix. So look at, there is the special form, right? It's not always general matrix. So we will have, because the second part will weakly converge 0, here second part weakly converge 0. This is the only problem we will face when we want to take the weak convergence of A epsilon, because it will have non-linear term with respect to eta 1. As usual for almost all omega, so we will get from the bounds weak convergence of U epsilon in solution space, and the weak star in because we need these things to show the initial condition satisfies the limit problem. So we will also take this convergence, and this strongly convergence needed in corrector results. Even though I listed here, it's needed only in corrector result. This also, this directly you get it, but when you do the other formulation, weak formulation, as I told, eta epsilon, when you take the derivative with respect to the space variable, then you don't get this weak convergence. There will be extra term. So depending on the method, anyway, you will get it the final result, the homogenization result, but here you don't get it the weak convergence. So the A star is nothing but A epsilon replaced the eta epsilon by eta omega. That is the as expected. That is the effective coefficient here. So once you have effective coefficient, that limit problem can be identified with this non-cylindrical domain problem. So wherever I defined eta epsilon in terms of the eta omega and eta 1 omega, now just you replace eta 1 omega by eta omega. So this is the corresponding problem in non-cylindrical domain. So once you assume ergodicity, even though you are assuming ergodicity, but still you will have this dependence on the event, because it will have this dependence. We don't talk about convergence of eta till now, right? Eta omega. So the limit problem of in case of the deterministic function, this is the limit domain. Okay. Now, yeah, I need to go here. Remember, this convergence you will get it. A epsilon grad U epsilon converges to A star grad U 0. But once you replace with the U epsilon with some other test function, you don't get A star grad of the test function. So you'll get the extra terms because it's needed when you want to show a corrector result directly. You apply the ellipticity of A epsilon, but then A epsilon will have the solution here, right? Instead of test function, you can take U0, so that will not converge to 0. So it will have extra term. That's I want to point out. For that, we need to do like the way parabolic equations derived for the corrector result. So first we will prove the energy convergence. Say energy of the function is defined by the oscillating domain. So this is the oscillating part from the epsilon dependence problem, and this is the limit problem energy. So for all omega belongs to O, we will have this convergence, strong convergence in C of 0t. It only depends on t because we have integrated on omega, full omega. So next, this is technical result because we want to approximate. As I told, you won't get this convergence directly. You'll have the extra terms. Like this is the extra term. And if you want to replace phi delta by u0, this will have the extra term in the convergence, weak convergence in case of a epsilon grad u0. So that part we are separating, but how we are approximating by u0 terms. So this is the approximation term which comes from u0 because we can approximate to u0 because it does not depend on epsilon. So this is the contribution comes from the oscillating part. So once we have this approximation, we will have the correct result. You use that to prove this. So this extra term needed here to show correct result. This will come from first part, and this is the contribution from the oscillating part. Still, it depends on smaller. Yes. So thank you.
Thank you, Sankar. Thank you, Sankar, for the talk. It was very nice. And so we should move on for the comments and all right now. So please, we have something like 5 to 10 minutes for the comment. So please go ahead and maybe Rajesh or Nandakant can say something. I don't know.
No, I just wanted to ask you again, can you please repeat what you did for the nonlinear term in this matrix, the convergence? So I didn't follow. I mean, you said you don't use two scale, but what is it that you use?
I used oscillating kind of test function, but which is not completely oscillating test function. So what I used it, first n minus 1 term, when you take a oscillating test function, you take full, right? Like n terms, which is comes from the right hand side x dot with the matrix. So oscillating test function, when we construct the oscillating test function, I use directly here because I have the special form, right? N minus 1 form. So I'll use up to n minus 1 terms, the oscillating function as directly, so that I'll prove the weak convergence directly from here. This part where it is, yeah, this part up to n minus 1 term. I use the oscillating test function directly. I don't consider the oscillating test function with the oscillations. Just I'll take as it is because of the special form of the matrix. Are you understanding? Or should I show something that what I did? I have the paper also, so I'll show. Yeah, look at here. I took the test functions like this. This is the oscillating test function what we choose in the right hand side x star gj with the matrix, right? A epsilon. So what I did, I choose directly wj equal to x times ej. So the coordinates, corresponding coordinates is the test function with the phi. So once you have this, what I am getting from weak star convergence and weak convergence, I'll directly get this relation up to n minus 1. That is, it's possible because of the matrix form. Once look at here, up to n minus term, it does not contribute anything from the derivatives. So, and especially this non-linear term, which won't occur, because we are talking about only n minus 1 dimension, n minus 1 cases you are taking. So this won't affect. So n minus you'll have this only derivatives of eta and the eta epsilon. So you'll get up to n minus 1 what do you want. The nth case, you need to apply this n minus 1 terms to show that it satisfies. That's how like I code it. But yeah, a little bit of calculations are there. I don't want to go there. But I used up to n minus 1 term what I calculated in between the calculation, and then proved it the nth term also it will satisfy. That's how I overcome. Basically, I avoided this n minus 1 term explicitly, the nonlinear term. Then I overcome using the first n minus 1 terms. That's how.
Yeah, thank you.
Any more comment, please? If somebody wants to comment something, please raise your hand and yeah, quickly, please. No comments? Okay, in that case, let's stop here and thank you very much to Sankar and all of you for attending the talk. Let's meet on next Wednesday at 12 p.m. in Chile, and maybe it's 9:30 in India.
No,
in the
10:30.
night. 9:30 is the time to start.
Okay. Okay, thanks.
Okay,
bye.
bye. Thank you. Ciao.
Ciao.
Okay, then Ravi. Oh, Ravi also left. Good. Shankar, it's fine.
Sir, how was it?
It's fine. You can have little more energy.
Okay.
As usual, your energy level it's fine. Good presentation, but little more energy.
Okay.
Maybe basics you spend more time. Maybe little more about your trick. I think many other places we use this trick. Somehow manage up to n. I don't recall. Some other basic analysis also somewhere we use. We study up to n minus 1 and use that to get the nth term convergence. Now I don't recall where we have done this kind of, and we do this many places.
Okay.
I could not recall where, not this one. There's a similar trick. It's a method of test functions, but you're managing n minus 1 term and then get the nth term.
Yes.
And this is this method. I mean, our basic study of PD is somewhere we have studied these kind of things.
Okay.
Okay. Ravi has left immediately before saying hi. Okay then. See you.
Thank you, sir.
Okay. Then. Yeah, I could say a little more and reduce little more about the basics.
Okay.
Little more energy while talking.
Okay.
Little more passionate and energy.
Okay.
Okay then. Bye.
Okay. Thank you.